Hello community, let's continue with scientific discovery with artificial intelligence. We have a brand new paper from Stanford University and it is called Paper to Agent. And yeah, you guessed it. The idea is that you have here any ArXiv paper, let's say on artificial intelligence or theoretical physics, whatever you like, and you just convert this into an MCP server so you have access with any interactive AI agent to this particular paper, to all the insights and every tool that you use. The complete code is available to you. So how do we build this from, if you want, a passive paper to an interactive agent with an MCP server? Now, the paper is called Paper to Agent, a framework that transforms your research paper from a passive publication into an interactive agent, and they demonstrated this for 3 different topics: for genomics, for single-cell analysis, and for transcriptomics. Now, I have to tell you, this was done by 4 departments from Stanford University, so maybe it is not that simple if you want to do this, but I wanted to show you this Paper to Agent, reimagining the research paper as interactive and, underlined, reliable AI agents for you to learn, have access to the complete scientific research, to the discovery process, to all the code, to all the tools and the insights. Now, they tell us here right in the front, hey, if you do not have the complete information, if you do not have the original code base, if the code base is incomplete or the code base is poorly documented or it contains some unresolved error, this will not work. It really depends that you have the paper, the ArXiv paper, then you have the complete, fully documented and fully operational and evaluated GitHub repo where everything is just perfect. And then if you are lucky and you are an expert in your domain, then you can have this MCP server. Great. So it is highly limited to expert knowledge, but let's say you do the research in your field. So you are familiar with methodologies, you are familiar with software packages, and let's assume everything in the GitHub is open source, so you do not have proprietary software that you have to pay for. Now, they made the code partially available. They have here an MCP server for the alpha genome, then 2 other MCP servers, and then what I was looking for was GitHub, of course, the Paper to Agent. Yeah, they have also here the agent code. The alpha genome agent is here available on Hugging Face here if you want to go there as an operative space. And the main question was, of course, hey, how you implement this? How can you go from a paper to an MCP server and to an interactive agent for learning with AI? Now, the idea is simple, no? You convert to a simple research paper and it's public GitHub, all the code base, all the documentation, all whatever is available, the data, into a production-ready MCP server. And then, if you have here a standard MCP server, you have an AI agent interface. You can have access with any LLM, any agent you like. Now, the authors tell us we have 4 stages. First, code base identification and the extraction here from GitHub. Then just check everything about the environment configuration. Is everything open source? Is everything available? Are there some hidden errors or whatever? Then the tool synthesis, and I'm going to talk about this here in the next minutes, and the MCP server generation itself. And of course, you have to have a final testing, refinement, and the deployment. This is followed up by the agent connection, and you can test it here live. So, main idea here, beautiful schema here from the authors from Stanford University. They say you have papers. Let's say with 1 paper. Let's make it easy. So we have 1 ArXiv paper, no? And what you want to build here automatically an MCP server with the content of this paper. So you have the manuscript itself. This is here the first resource if you want. Then there's somewhere a link to the GitHub code repo. Beautiful. Then there should be a link to additional data, the data sets, the raw data, all additional data cleaning, everything that happened here in the complete data cleaning pipeline. You have to have access to each and every item, otherwise it fails. And then the ideas have access to all of this, and then you build here automatically tools. So you extract here from the software particular tools. I'm going to show you this in detail. Plus, we also have then given prompt, an optimized prompt structure here for specific, let's call it scientific tasks, or reproduce here a particular visualization that was published here in the ArXiv print. So this is exactly what we want. MCP tools, MCP resources like the manuscript and GitHub, and then MCP prompts to be immediately interactive and executable. Then let's say you put it somewhere here on Hugging Face here, connect to any agent here. And then you say, oh, great. So we have this new methodology or this new idea. So here is now you say as a user, hey, here's now my own data set, but please apply here this new paper methodology, all the new code optimization, and just show me here, for example, the data analysis now based on my primary data set. And in theory, the agent should say, hey, absolutely here, everything is done. This is the result with the optimized code, with the new scientific insights. So enabling scientific discovery through the paper agents. This is the theory. Now, let's go to the implementation. How do we do this? Of course, we need some multi-agent system, but how is it done? Now, Stanford tells us, we have 5 agents. So we have the boss, the orchestrator agent, and then we have 4 sub-agents. And those 4 sub-agents are the environment manager that makes sure everything is operational, a tutorial scanner, I will explain this in a second, the tutorial tool extractor implementer, and you see, yes, this is an academic one, and then we have test, verify, improve agents. So let's have a look. Before we jump into an agent, what is the overall flow that we're going to have a look at? So in the ideal scenario, we have here one single ArXiv paper with a code base somewhere on GitHub. Everything is available. Everything is publicly. You have an MIT license, no problem at all. So extraction agent, beautiful, extracts you the complete code base, analyzes the code, tries to find here particular software packages, let's call it tools, that are specific for this task. You have another agent that just verifies that the code is indeed valid and executable. Then we have a configured environment ourselves, and then we bring everything together. We have a testing agent that makes sure everything is working together. We create our MCP server, and somewhere remote server Hugging Face, done. Now, the flow itself, the authors tell us, consists of 6 particular steps. First, locate and download, if we have the ArXiv paper, now the GitHub repo, the complete code base, the complete data set, everything that they used. Then let's have a look, can we reconfigure the complete environment setup? Do we have all the data? Do we have access to all the software packages, to all the training data, to all the environmental data, everything? Then there's something interesting. The next 3 steps, as you see, they talk about a tutorial discovery, a tutorial execution, and then a tool extraction and implementation. And then the last step is we just build an MCP server. So you immediately understand those are the 3 important points that we have to understand. Now, talking about GitHub, you see just 17 hours ago, I'm really a little bit early here, but they are hopefully filling up now here, because if you look at it, you see the source code will be released soon. So this is something that is not really great, Stanford University. You say the code is available on GitHub, and then if we go to GitHub, it is not available. So I hope whenever you see this video, the source code is available for you. Now, they give us here 3 beautiful examples, as I've shown you. Let's have a look here at the tissue MCP server. What you can do, what is the idea? You have a paper, let's say a Nature publication on ArXiv, whatever you have. So you want to build now an interactive learning agent for you that provides here the theoretical insights and the complete algorithm, the complete code base, the complete data set that were used, and the complete visualizations or graphs or everything. So MCP tools, MCP resources, and MCP prompts. You want to have everything here constructed for you automatically. And then you do have an agent that has access to this MCP server and you say, hey, here are my data, and the performance is done. Now, of course, if you say, hey, based on the MCP server, what can you do? What are the required input? What is the expected output? Since we operate here with an agent, let's say we go with an, standard LLM, you can have here also about the theoretical ideas, how the methodology is constructed, designed the test. It is just not about here coding. And then produce the identical results to those of the human researcher. So you see if you have data, you get then very similar ideas. You can compare maybe then to the published result with your own data set. So the idea is beautiful. And then you have the MCP server, you have now the tissue MCP resources. They provide you with a structured format for, let's say, transcriptomics that you can use here with your particular data, or you filter the data for your particular selection of species or whatever you want to do. And you get here also beautiful results as published as a reference here for the community. Now, let's come back to the server architecture and how we build the server, because I think this is the most important thing. Server comprises here 3 components, the tools. Those are just executable functions that are encapsulated here in the ArXiv methodology with some pre-configured, let's say, Python environments here. And each tool includes here a direct link to the original code here in the GitHub repo. Then the resources, this is everything that is static. No? The manuscript text itself, all the data sets, all the tables, all the figures that were produced, everything you want to be able here to regenerate here completely just with input data and the available published code, the results. You just want to validate it. And then, of course, you need for this the prompts that were given since we are working with AI systems. So instructions here guiding here multi-step workflows. We have here 5, 6 agents. How they work together, how was the exact prompt sequence. You want to have a clear reproducibility, and you want maybe reduce here the prompting complexity, but more about this later. So let's focus, I think the tools are the most important because these are the new software elements that we're gonna get. So, and you remember I told you from the flow, we do have those 3 elements, the tutorial discovery, the tutorial execution, and the tool extraction. How is it done? At first here in the workflow, it really incorporates here a tutorial discovery step where we have one dedicated agent that is trained only to do this. A tutorial scanner sub-agent scans here the repo for reference materials, such as, are there any tutorials already in the published literature? Can I extract some example scripts here from the GitHub? Are there any listed educational resources I can integrate or refer to? So everything identify candidates that are suitable for any kind of a tool creation depending on the complexity and your domain knowledge. And then this is followed now if we find something that says, hey, yeah, we have here some educational resources. So tutorial, execution, auditing, and then finally a tool extraction from those data. So where the core methods are translated then from the paper into reusable functions, let's say Python, C++, whatever you prefer. And then we have another dedicated agent, a very specialized agent here, the tutorial scanner, for reviewing here the public code base to identify and organize educational resources. So what it does, it scans here the available materials, distinguishes here some real tutorials from other files that are not as necessary, and highlighting those that are most useful for reuse. What function can we extract? What tools can we build here? What is here reproducible? And then this particular agent produces here clear summaries and clear reports, input-output structure, providing here structured view of which resources are worth keeping, which can be set aside, and maybe even here the reasoning behind it. And then comes the next specialized agent, the tutorial tool extractor implementer. Beautiful name, Harvard. It simply converts here this kind of tutorial into a tool. This is all there is, into a reusable tool. So whatever coding LLM you go with, hopefully it is able to perform this task. Remember, we have here 4 sub-agents and 1 orchestrator agent. So we have 5 agents that are interconnected and interoperability. So I hope none of those 5 agents LLM has any hallucination while you code this. So our extractor implementer here reviews the selected tutorials, identifies the task, the generalized beyond example data, and implements each as a clean, single-purpose function. So we have input defined, output defined, default defined, environment defined. We have now single function and we build tools out of this. Parameters hardcode values, enforces here file-based input, saves essential result into figures, and returns a standardized summary of the produced artifact. Its goal is to simply produce a library of all the function from all the publication, so we can reproduce the tutorial results on the original data, on the original training data and everything, while remaining ready to run on the new data set. So this is the dream that we all have. The publication is just gorgeous. The documentation of the code is 100% perfect, and code is operational, everything is open source, everything is documented, no errors at all. No runtime errors, nothing at all, no dependency errors, nothing, everything is perfect. Then maybe those 5 agents can extract, if they have been trained properly, the most important tutorials or software sequences, understand from the thematic description of the particular scientific task that this would be a mathematical function, a mathematical tool, a mathematical function that we should include in our code library because we're gonna reuse this. So you see there are a lot of if, and if this would be true. So let's come here to the last, the very specialized agent, the test verifier improver. It creates now this implementation, it runs the implementation, and it refines tests for this tutorial implementation. It uses only the tutorial's own examples here to ensure complete coverage and a faithful reproduction of all the numerical and visualization results. But this is only possible if you really have provided here the complete dataset for open source usage. So the agent runs here in a loop of generating the test, executing everything, diagnosing here failures if it happened, and then this agent is here such a genius agent that it can apply, of course, here all software and coding fixes, that whatever is not working, now it will work immediately. Isn't this a beautiful theoretical world? If it continues to fail, here Stanford tells us, you know what? In the MCP decorator, we just remove this function. We remove here this, if you want, tutorial, this ability to calculate here whatever you are interested in, because we just integrate everything in the logs for transparency, but we just want operational code. Now they decided here to go here with MCP servers with Claude Code. Of course, MCP, remember, here was originally generated here by Anthropic, so no wonder that they go here. Let's call it a real good compatibility between MCP and Claude coding, but they also say they are working on alternatives like here a Gemini CLI, but for the moment, it was done with Claude Code. So I could not see here because the source code is still missing in their own GitHub repo, where they say it is so important to have a complete GitHub repo. It is still missing, Stanford. So I assume that they were working with Opus 4.1, but I have no proof, nothing, no documentation. I have no idea what coding LLM they implemented here. But let's go with Opus 4.1. So you see, from the idea, you understand clearly, you have so many research papers and hopefully code published. So you want to make this interactive. You want to bring it to life. You want to bring it to a pool of agents that have now a much better understanding, that have now much more software repos where it has been tested, it is working, the data are there. So you just input your data, your experimental data, and you don't have to care about here how to design the experiment, how to design here the software components, which libraries to use. Everything is done for you by AI. But I would say for the moment, if you are in Stanford and you have 4 departments working for this demonstration, yes, you can set it up. Yes, if the source code would be available on a GitHub, we could have a closer look. But for the moment, we just have to trust your Stanford University that this is your trajectory into the future of doing research with the help of AI, learning and discovering new scientific insights with artificial intelligence. I hope you enjoyed it. It would be great to see you in my next video.